union of these two singletons. And then we can define an arithmetic operation, can define a binary operator that takes in two integers and gives you one integer. So it gives you the result. It's just summarizing in code what I've said. If the two are equal, the result is equal to the first. So this is true if both are +1, you do the union of two of the same singleton, you get the same singleton. 2 are -1, same thing. If the two are the complete set, then you get the complete set. Can you get the empty set? Well, if you get the empty set for one coordinate, it means that your set of possibilities is empty, and so all coordinates would give you the empty set, and so we deal with that later. So if the two are not equal, it means that either one of them is the full union and the other one is a singleton, in which case the union is the full union. And so that's one possibility. Or you have the two singletons and then the result is the full union. So that's what you get. Okay, and then so we're representing the semantics of a set union with the integer 0, -1, and +1. So it's not the complete thing, but for our purposes it's fine. And then, like I said, it's possible that a footprint be empty. So if you have the empty set for each components, the convention will be that that if you pass it in, the address that you pass is going to be the null address. This is how this function will detect. This function is basically taking the pointwise function and applying it to the whole thing pointwise, so making it the full semantics. And by convention, or by design, I should say, this is like a hard constraint. The second element will never be null. The first might be null, but the second will never be null, because we will start with something that's null, and we will only add something when it's not null. And we will always, so this thing will be what we the total footprint, and this is the thing we want to add to the total footprint. And yeah, so if it's null, we have to allocate some memory. You can prove that there will only be one such allocation. Alright, so if we really cared about performance, we could have our custom, like our own memory management unit, and then we could have some spare, 8 bits, not 8 bits, 8 slots in memories, 6 slots in memories dedicated to that, and when we start with null, and then instead of allocating from the heap, we would just allocate from our own pool of memory, because this only happens once. Well, what's going to happen is that we start with null, and then whenever we add something, we add it on the total. So we never add null, and once we get something non-null, which means it's not the empty set, we can't by union get the empty set. So this is what's going on. So right now we don't care because again, performance is not critical. If you wanted to do it more strictly in terms of memory without touching the heap, you could do it here. and then if it's null, then the result is simply the thing you've added, which is the second. And then if it's not null, then you have the two things. And this thing is saying that this line is saying that we're not going to create a new footprint. We're going to modify the first footprint. Okay, so it's kind of if this pointwise footprint semantics had some side effects. We know it doesn't, but if it had some side effects, we could be in trouble because we could be kind of polluting the thing. You know, you have like these pointwise things to do, and we could start doing the first and then pollute the rest, and then the results wouldn't be correct. But because we take in the two things and then we compute the result, then we put it here, and then the other things are not affected, and we just go through like that. There's no possibility for side effects in this case. Okay, so this line, by the way, this is what makes the pointwise footprint semantics pointwise. It's just you look at, so the indexation here is the same indexation that indexes the pairs of coordinates with just one index. Okay. So here we have a function which is a predicate, which is, so it returns either 0 or 1 to signify either false or true. But 0 and 1 are integers, and so it's just an integer. Okay, so what it does, it takes two vectors and it computes their scalar product. So you start with 0 and you add the product of each component. That means you take the sum over the product. And then if it's 0, we return 1. If it's not 0, we return 0. Okay? So 0 as a result of orthogonal Q means not orthogonal. 1 means orthogonal. Okay. And then the product matrix is the thing that allows us to know which vectors are orthogonal to which. So if you pick a pair of vectors and then you generate the orthogonality constraints and look at the set of possibilities, this process is the same as multiplying each of these two vectors with all the other vectors, and then simply selecting those vectors which are orthogonal to both. So if you do the product matrix, this is what you get. So each row corresponds to a vector. You can think of a vector corresponding to a orthogonality constraint, and by vector I mean pair of parallel vectors. And each column corresponds to a potential vector or pair of vectors that you would like to add to your set of possibilities. And so the diagonal is always going to be 0, because vectors are never orthogonal to themselves unless they are the null vector, and the null vector is not in the set of vectors we consider. So it's not a space of vectors we are considering, it's just a set. And so here you see that the fourth vector is orthogonal with the first vector, and you can see that it's symmetric with respect to transposition. So it's like this equals to this, and this equals to this, and so on. Okay, so if you take a pair of vectors which happens to be the first two vectors. Okay, so you're taking a pair of non-parallel vectors, and it's the same. It's going to give you the same answer if you flip any of the vectors or both. It's going to be the same. Okay, and then each column of this line, of this rectangle here, corresponds to a potential pair of vectors. And every time you have 0, it means no, it's not orthogonal. So if you want to look at the vectors that satisfy both constraints, this one satisfies the second constraint, this one satisfies the first, this one satisfies the second, first, second. Okay. You can actually prove, or you can modify this code to prove this. Actually, it's already within this matrix. This matrix is already a proof of that. But okay, so here's the statement: if two vectors are not orthogonal, then in this space, if two vectors are not orthogonal, then their constraints will never be mutually satisfied. So if you have this pair of vectors, there's no vector that satisfies both being orthogonal to the first and orthogonal to the second. So in R3 and just real regular old space, okay, if you have like three vectors like this, and then the first two are not orthogonal, but they're in the same plane, then so like this is the x-axis, this is a vector x plus y or something. This vector is still orthogonal to both, so you can still be orthogonal to both of these, even if they are not themselves orthogonal to each other. Now we're in 4D, but the problem is that we're restricted to plus and minus 1. And so if you have two, so if you take the pair of vectors, the first and the second, first and third, then you can see first column it satisfies no constraint, satisfies the third constraint, no constraint, first constraint. Okay, again. You have a 0 there, which means that the first and third vectors are orthogonal, so there's no overlap. But if you look at the second and third, then you have a 1 here, and that doesn't immediately disqualify them to have overlap, and in fact every pair of vectors which is orthogonal has exactly 2 overlaps in this case. Okay, and so how does that work? Okay, so first vector, so now you look at these second and third. Okay, so first vector does not satisfy any, second satisfies 1, and no, so 1 constraint, 0 constraint, 2 constraints. So the vector corresponding to this column would be in the set of possibilities for these two, for this pair of vectors here, and so would this column, because you have 2 1s. Okay, and so how do we compute this? It's pretty easy. We simply traverse this matrix. So we need 2 indices going from 0 to not para, and we just, for each integer we get a vector, and for each pair of vectors we compute whether or not it's orthogonal. So it's not the product matrix, it's the orthogonality matrix, I guess. And because of the symmetry in the problem,